All right. So introducing geometric sequences, we're going to explore some growing and shrinking patterns, which is if you see constant's not the right word, but there is a pattern with how these things grow and shrink. All right. So I just want you guys to take 30 seconds. Just look at these lists of numbers. Okay. Just look at these lists of numbers. So you got 4 different sequences, and I want you to just pick one of them. All right, and just think about what you notice and like what you wonder, meaning like what do you wonder, like what's going to happen next, okay, in these sequences. All right, just take 30 seconds. There's no right or wrong answer. I'm not going to have you guys tell the whole class like verbally. All right, but I want you guys to just kind of take a look at the list. Okay, about 10 more seconds. All right, so you guys are looking at this list, and maybe one of the things that you guys noticed is that the first 2 lists, the numbers are getting bigger, and the second 2 lists, the numbers are getting smaller. Okay. And while we're not adding the same amount to each number as we're going up on the first 2 or subtracting as we're going down, it does look like there's something consistent that's happening. All right. Um, these smaller numbers are probably a little easier to work with in our second sequence, but it looks like I might be multiplying by the same thing to get the next number. So like 2 times 4 is 8. 8 times 4 is 32. 32 times 4 is 128. Numbers get pretty big. It's harder to do those unless you have a calculator with you. Okay. Um, yeah, it's looks like if I got a bigger number, 1,000 is a good number to start with because it's a nice round number. 1,000 divided by 2 is 500 because it's half, and 250 is half of 500. So 500 divided by 2 is 250. 250 divided by 2 is 125. Okay. And then maybe when you're looking at this list, some things that you might wonder, why do all of these start with an even number? Does it have to start with an even number? Um, will all of these sequences eventually have decimals, kind of like this third sequence does? Um, but these are just things that if you are given a sequence that you guys can be, there's no right or wrong answer to these questions of what do you notice and what do you wonder. But they're all good questions to ask yourself when we're trying to decipher what the pattern lies within the sequence. Okay. All right. We're going to do a little activity here. At least I'm going to do the activity. And and then I'll show you guys. Now, just so you guys can see, I really do have a sheet of paper here. Okay. It says Claire takes a piece of paper, cuts it in half, then stacks the pieces. She takes a stack of 2 pieces, then cuts it in half again to form 4 pieces, stacking them. She keeps repeating the process. The original piece of paper has length 8 inches and 8 inches, has length 8 inches and width 8 inches. Complete the table. Okay, so our goal is to complete this table. Okay, so our piece of paper, all right, and I'm gonna I'm going to show you guys here. I've got the sheet of paper, 8 by 8. Okay. In fact, I've actually got two because I thought I may mess up one time. So now I've got a backup. All right. So I got my sheet of paper here. And what I'm going to do is I'm just going to cut it directly in half. Okay. Well, I guess I'm going to go ahead and go back to my screen, sharing my screen, but all right. So the first thing was zero, number of cuts, 0 cuts. So my first sheet of paper is an 8 by 8 piece of paper, and I've only got one of them. All right. So how many? What's my number of pieces? I got one. All right. So I'm gonna go ahead and put down a 1 over here for my number of pieces, and the area in square inches of each piece. Well, my one piece was an 8 by 8, and you get the area by multiplying the length times width. So that would be 64. 8 times 8 is 64. Okay. All right. Let's go ahead. Let's cut this in half. Try and be pretty precise with this. All right. I stack them on top of each other. Well, I know I've got 2 sheets of paper now. So after one cut, we've got 2 sheets of paper. And the area, well, since it used to be an 8 by 8, and when I cut it in half, now it's 4 inches by 8 inches. So 4 times 8 is 32. So it has, each sheet of paper will have an area of 32. And that makes sense because 2 sheets of paper, they'd have to add up to what it was when I had 1 sheet of paper. So 2 times 32 would be 64. All right, let's go ahead and cut these in half now. Now, when I cut them in half this time, I'm going to have 4 squares. All right, put them right on top of each other. I've got 4 squares. Each of them are 4 inches by 4 inches. All right, so I got my 4 sheets of paper. And 4 by 4 inches, 4 times 4 is 16. All right, you guys can probably already see the pattern that's happening here. Without doing any more cuts, I should be able to figure out some of these next ones. 3 cuts, number of cuts 3. So it looks like I'm doubling every cut I make, I'm doubling the number of pieces. So I should go up to 8. But each time I cut them in half, I'm cutting their area in half. The sheet of paper I'm laying on top of each other, the top one is going to have an area that's half of what it was before. So instead of 16, it'll become 8. On the 4th cut, I'll end up having 16, and each one will have an area of 4. When I go to cut it again, I'll end up with 32 sheets of paper, and the area will be an area of 2. All right. Now I could keep going, and I kind of want to go a couple more steps because I want to see when this becomes a decimal. So 6 cuts, 7 cuts, 6 cuts, I'd end up with 64 sheets of paper. Each would have an area of 1, 1 square inch. And then the next one, we get to 128 sheets of paper and 0.5. Each would have an area of a half a square inch. Okay. I don't know. This reminds me. I know there's a math problem that talks about a sheet of paper, and it's not a puzzle, but it's a interesting fact. And they talked about if you were to take a sheet of paper and like do this, like keep cutting it in half, it's not as many cuts as you'd think before the paper would become thick enough to actually travel like into space, because it just the doubling of the thickness of the paper every single time would, now it'd probably be really, really tiny, but the doubling of it after even something like 20 or 30 cuts, it's really tall already. All right. So this is our table here, and we do see a sequence. We see in the number of pieces of paper, it is growing pretty rapidly, whereas in the area in square inches, it is slowly well, I should say, is pretty quickly getting closer and closer to 0. All right. So I think we can figure out how to find the remaining. If we were to say how many cuts would there be on cut number 8, well, we could double our number of pieces. We could divide our area in half again. Okay. So I think we got an idea of what the pattern looks like here. All right. So we've got two graphs here. Let's talk about how we could plot what we were doing here on these graphs. It says on the given axis, sketch a graph of the number of pieces as a function of the number of cuts. All right. How can you see on the graph how the number of pieces is changing with each cut? So if we got number of cuts and number of pieces. So with 0 cuts, all right, with 0 cuts, we were at 0, all right? Or sorry, when it was 0 cuts, we were at 1. So it'd be just above the line. At 1 cut, we were at 2, so still pretty low on this graph. At 2 cuts, we were up to 4, so just below this first line, because each line going up is 5. So 4 would be just below that line. 3 cuts, we were at 8, so now we're a little bit below 10. 4, we would be at 16, so we're just above this third line. 5 is at 32, we're jumping up a little quicker now. We're over here at just over 30. And 6 will be at 64, which will be up here somewhere. Because 50's here. 60, I'm just gonna put a point up here that's about it, close to where 64 would be. Okay. So we see that it starts growing slowly and then it gets steeper pretty quick. Okay. All right, let's do the same thing with our area in inches. So we started off at 64. We had 0 cuts. 1 cut brought it down to 32. 2 cuts down to 16. 3 cuts was down to 8. We're getting pretty close to the bottom now. 4 cuts was at 4. 5 cuts was at 2. 6 cuts was at 1. All right. Now these graphs they're kind of similar, all right, in that this one started slow and got steeper pretty quick, where this one starts really steep and then gets shallower as we get closer to 0. Okay. All right. And these actually represent some growth, and this one we call a decay if we were talking about them as exponentials. All right. Now we were able to identify the pattern. Okay. Now we had a physical thing with us, these sheets of paper, okay, that kind of helped in visualizing the area shrinking by half each time. And also the number of sheets of paper that when I would stack them back up, I was just doubling the number that I had previously. Okay. But we should be able to identify some of these sequences, all right, without having paper. All right. So what I want you guys to do is take a look at these. I'm going to give you guys about, I'll give you a couple minutes, 2 minutes to work on A through E. And what I want you to do is I want you to figure out what should go in these blanks. Okay. I want you to try and figure out what should go in these blanks. Don't worry about D. For some reason, that one didn't come through. All right. But go ahead, give A, B, C, and E a try. Try and figure out what those blanks are going to be. If you have something to write with at home, then just rewrite the sequences with those ones you're putting in there circled so you remember which ones they are. Okay. Again, I'll give you 2 minutes. So right now it is 8:06, probably at 8:07 or 8:08 or 8:09. I'll stop you guys and we'll go over this sequence. All right, so it looks like in the geometric sequence in A, looks like everything, looks like it's doubling. If I go from 1.5 to 3, I have to double it. From 3 to 6, I would double it. So 6 to the first blank, doubling 6 gives me 12. And just to verify, that looks like it fits because when I double 12, I get 24. And when I double 24, I get 48. All right, we'll come back to the growth factor after we get these blanks filled out. All right, 40 to 120. All right, looks like I have to multiply by 3. I triple the number. 120 times 3 is 360. 360 times 3, calculator would probably be helpful. 1080. Or 1080 times 3 is 3,240. You can see how quickly these numbers can grow. That's just 5 items in, 5 terms in, and we're already in the 3,000s. All right, now C is going the other direction. It's getting smaller. But what I like about this is it's just getting smaller. It's like we're taking zeros away. Starts at 200. Then we take a 0 away, we're at 20. Take another 0 away, we're at 2. All right. Or another way to look at it is it looks like we're moving the decimal place 1 place to the left every time. So we move it to here, it becomes 20. Move it to here, it's 2. So if we move it from here to there, it becomes 0.2 or 0.2. Move it one more to the left, we get 0.02. Move it one more to the left, we got 0.002. So these numbers are getting pretty small. All right, and E, 24 to 12, 12 to 6. Okay, these are they're going by half in size here. So 24 divided by 2 is 12, 12 divided by 2 is 6, 6 divided by 2 is 3, 3 divided by 2 is 1.5. Okay, this actually looks like our pattern up in A, just in the reverse. Let's talk about growth factors, okay? So we're gonna put, for each sequence, find its growth factor. Now the growth factor is the number you would have to multiply your term by to get the next term, okay? So A is pretty straightforward. I'm multiplying each term by 2 to get the next term. So my growth factor would be 2. All right. B, we figured out we're tripling it. So we're taking each term and we're multiplying by 3. So our growth factor would be 3. The harder ones are C and E because we're not multiplying by a whole number here. All right. In fact, I'm going to go down to E because I think E is a little bit easier to see to start. But we were dividing by a number. But we also know that multiplication and division are inverses of each other. And dividing by 2 is the same thing as multiplying times the inverse of that, which would be 1/2. Right? Because remember, that's 2 over 1. So the same thing, if we could be multiplying by the inverse, which just flip the fraction, becomes 1/2. So our growth factor here is going to be 1/2 because I'm going to multiply each term by 1/2 to get our next term. Okay. When we're thinking about C, when you have a problem like this where we're essentially moving the decimal place 1 over, I like to think about it going the other direction. If I've got a number like 5, right, and I move the decimal 1 to the right and it becomes 50, well, what did I multiply 5 by to get 50? I multiplied times 10. All right. If I were to multiply by 10 again, I just add another 0. All right. Now in this one, we're going the other direction. We're starting with the bigger numbers and we're getting smaller. So we're dividing each of these by 10. Well, remember, if it's divided by 10, that fraction is 10 over 1. That's the same thing as multiplying by 1/10. Okay. So our growth factor for C would be a growth factor of 1/10. All right. We're multiplying each term by 1/10. And you guys can kind of see where a calculator is going to come in handy with some of these. because there's going to be some numbers that aren't going to be as easy to compute, especially some of these fractions. And a calculator would be helpful when you're doing those multiplications to get the next terms in the sequence. Okay. All right. So I want you guys to start. This is our last one for you guys to try. It says, here's a sequence, 500, 100, and 20. All right. I want you guys to think about why this sequence could be a geometric sequence and what the next term is. Now, when you're thinking about if it can be a geometric sequence, you got to know that there's a growth factor, okay? So think about what your growth factor would be if you think this could be a geometric sequence. And then come up with that next term. I'll give you guys a minute to work on this. We're pretty much done. We just have a couple slides left, and they're really just terms after this. So we're going to be done in a few minutes. But if you guys could give this last one a try for me, give you 1 minute. All right, so taking a look at this sequence, it looks like it's obviously getting smaller, 500, 120. I like to think of things, it helps me just to, if I'm looking for a growth factor, I like to think about the division first. I'm going to go with the smaller numbers and see if it works for the bigger numbers. But I know that 100 divided by 5 would give me 20. All right, 100 divided by 5 would give me 20. Let's see, 500 divided by 100 would also be 5. So it looks like by dividing by 5, I can keep going. So for the question 2, I could 20 divided by 5 is going to be 4. All right, so I think I'm good on that one. So the next term will be 4. Growth factor, now it's not division. So instead of dividing by 5, our growth factor would be 1/5. Okay, 1/5. I'd multiply each of these terms by 1/5. Okay, to get my next one. All right, now a couple of you have had a question. You're kind of like, what is a geometric sequence? Like, and actually, I actually looked it up the other day. I'm like, why is it called a geometric sequence? And they actually get that term from the geometric mean from right triangles and finding the hypotenuse. So it's a complex answer. I didn't actually fully understand the answer either. But it does have something to do with right triangles and finding the geometric mean within right triangles. But the definition we're using, it's a sequence in which each term is a is a constant times the previous term. Okay. So it's basically you're using that consistent growth factor, right? Each time you move from one term to the next. And that means that we're going to be multiplying by the same thing from one term to the next. All right. It's our geometric sequence. And that's really the only new term that we have today, other than growth factor, which our growth factor is that thing we're multiplying it by. Okay.